So last time we got into 3.6, right? 3.6, we talked about the two main forms to apply L'Hopital's rule. 0 over 0 or infinity over infinity. Up until this point, 0 over 0 we could factor, right? Infinity over infinity we could deal with in other ways by looking, if they're both polynomials, looking at the highest term of x in the numerator dividing by the highest term of x in the denominator and making a conclusion. So now we're looking at a little bit more complicated functions, maybe like an exponential over a polynomial. And when we did that, it turns out we found out we have two theorems in our book that lets us make a conclusion right off the bat. If I have a polynomial over an exponential, I'm always going to go to 0. If I have an exponential over a polynomial, I'm always going to go to infinity when x goes to infinity. Okay, so we did a couple examples that we've done before, we've manipulated before. The sign of 2x over x as x goes to 0, we know the answer is going to be 2. We can show the answer to be 2 by multiplying top and bottom by 2. And then from the squeeze theorem, we know sine of 2x over 2x as x goes to 0 goes to 1. So then our correct answer here would be 2. Or we can apply L'Hopital's rule. It's 0 over 0. Apply L'Hopital's rule. Evaluate the limit to be 2. Same thing with the polynomial over the polynomial. If I plug in 2 and I get 0 over 0, that tells me 2 is a factor. Factoring quadratics, pretty straightforward. I can factor that, or I can apply L'Hopital's rule. Differentiating polynomials is easier than factoring in most cases, right? Unless it's a nice quadratic. So here, if I apply L'Hopital's rule, I get this form. If I plug in 2 here, I get 4 over 6, which is 2 over 3, which would be the same thing as if I factored it and plugged in 2. So the next indeterminate form we talked about was when I have a function going to 0 times a function going to infinity, or plus or minus infinity. So these are conflicting results here, and I have two options. I can pull the x down to the numerator and make the power negative, or I can pull the ln down to the numerator and make the power negative. So deciding on which one to do, I just picked the top one was going to be a lot easier to differentiate than the bottom one. So doing that, I end up with a fraction divided by a fraction. I flip and multiply, and then I am left with minus x. So the limit as x goes to 0 of minus x is going to be the same as the limit as x goes to 0 of x times ln of x. So it turns out the limit here is 0. So these conflicting functions, something going to 0 and something going to infinity, when x is going to 0, it turns out the 0 overpowers the infinity, and the 0 wins out here. But that's not always the case. And then last time, we did the example where we might have to evaluate some trig functions at some points to know what sine of 0 is, sine of pi over 2, pi over 4, pi over 3, pi over 6, things like that. So when I evaluate this, I get a 0 times infinity. So I want to manipulate one of them to get 0 over 0 or infinity over infinity. And I decided that the secant, since secant's 1 over cosine anyways, I'll just put it in the denominator and call it cosine. So I rewrite secant of 2x as 1 over cosine of 2x, and I have this function, which is a true 0 over 0. I apply L'Hopital's rule, so now I need to know the derivative of trig functions. And then I evaluate this at pi over 4. It turns out this is going to 2, and the bottom is also going to 2, so the whole limit goes to 1. So you have to be, on 3.6, really you have to be careful in evaluating limits. So being able to plug in a point to know, is it going to 0, is it going to infinity? So know functions like e to the x, ln of x, tangent of x, tangent inverse, secant, cosecant, things like that. You have 1 over something going to 0 that goes to infinity, right? And then on top of that, identifying it's in a correct form, applying L'Hopital's rule correctly, and making a conclusion. And you might have to apply L'Hopital's rule more than once. Okay, so I think we're caught up to where we left off. And the next type of indeterminate form we're going to talk about is when I have infinity minus infinity, right? We hadn't had a chance to talk about that one. Okay. So today is we're going to talk about indeterminate forms of type infinity minus infinity. So infinity minus infinity could be positive infinity minus positive infinity. It could be minus infinity minus minus infinity. Maybe I'll write it like this. All right? It could be positive infinity plus minus infinity. It would be minus infinity plus positive infinity. Those are the 4 indeterminate types. What are not indeterminate? Would be something like positive infinity plus infinity. What's positive infinity plus infinity? It's infinity. And then positive infinity minus minus infinity. Here I have minus infinity minus minus infinity. So it's really minus infinity plus infinity, which would be a conflict. Here, plus infinity plus infinity is not a conflict. Minus infinity plus minus infinity ends up being minus infinity. And then minus infinity minus plus infinity is minus infinity. So these are not indeterminate forms. If you have something that's a function going to infinity plus a function going to infinity, your answer is infinity. So don't do any more work on it. The indeterminate types when you have conflicting results, like plus infinity minus plus infinity, or minus infinity minus minus infinity, because that's really minus infinity plus infinity minus infinity, and minus infinity plus infinity. Those are the 4 indeterminate types. So let's look at an example. If I take the limit as x goes to 0 from the right, 1 over x minus 1 over sine of x. So what type is this? Mm-hmm. It's infinity minus infinity. So I can't do anything with infinity and minus infinity. If I'm going to apply L'Hopital's rule, it has to be infinity over infinity or 0 over 0. So what's a suggestion I could maybe get this into one fraction? How would I go about that? Common denominator, right? So I would get, this would equal the limit as x goes to 0 from the right of sine of x minus x over x times sine of x. Right? So I didn't change the expression, I just simplified it, so I found a common denominator. Now if I plug in 0, what do I have? Sine at 0 is 0, minus 0 is 0, and then 0 times 0 is 0. So I have 0 over 0, which is an example of a type I can apply L'Hopital's rule directly, right? So applying L'Hopital's rule here, I'm going to have to use the product rule when I differentiate the bottom function. So L'Hopital's rule tells me the limit as x goes to 0 from the right. What's the derivative of sine of x? What's the derivative of x? And then what's the derivative of x sine of x? Right, so I heard it 2 different ways, but I think it was correct. So if I take the derivative of x, hold sine, plus the derivative of sine, hold x. Derivative of sine is cosine. So I get this relationship. x goes to 0, cosine of 0 is 1. So I have 1 minus 1, which is 0, over sine of 0 plus 0 times 1. So 0 plus 0, which is 0. So this is still 0 over 0. So it tells me I need to apply L'Hopital's rule again. So L'Hopital's rule equals the limit as x goes to 0 from the right. What's the derivative of cosine of x?
Minus sine.
What's the derivative of 1? 0. So then I differentiate the bottom. What's the derivative of sine? Plus the derivative of x cosine, which would be cosine plus minus x sine, right? So you guys see how I do that? It's really adding a layer of a step here, because I can expect you to differentiate a function like this. I expect you to differentiate a function like this, right? So you should be able to differentiate both of those. Now if I plug in 0, what do I get? 0 on top, right? 0 over 1 plus 1 minus 0. So it'll be 1 plus 1 minus 0. So that would be 0 over 2. What is 0 over 2? 0. And I'm done. And I've made the conclusion that infinity minus infinity in this case is 0. But it's not always the case. It could be 5. It could be infinity. It could be minus infinity. Here it's 0. They cancel each other out when we go to 0. So your approach on problems like this, when you have infinity minus infinity, is to find a common denominator. And once you do, you have 0 over 0 or infinity over infinity. Question?
Do you just put the on the bottom there, that negative sign? That's obviously negative sine of x, but you put that negative 1 out in front.
Yeah, because I want to
So
make
you
sure
don't
I know it's
subtract.
minus x sine of x and not x minus sine.
Okay.
So
Because
the
it's obviously
negative
they're
is-
multiplying, so
Yes.
it just do it. Okay.
Yes. So if you're careful the way you write it, you're fine. But if you put x minus sign, sometimes you interpret it as taking x minus the sign versus minus 1. Yeah. Another form that might come up, see some examples. Okay, this is number 35. Okay. L'Hopital's rule is all neat and everything. However, it's not always the best approach. So we're going to look at an example that's in the form infinity minus infinity, and you're going to simplify it, and it turns out L'Hopital's rule is not the best approach here. The best approach would be doing the techniques you did in Chapter 1 for evaluating limits. So this is number 35. It's a written homework problem, so if that motivates you guys a little bit to pay attention. Let's look at number 35. I'm taking the limit as x goes to infinity of the square root of x squared plus x minus x. So what type is this? Yeah, if I plug in infinity, the square root of that is infinity. So this is type infinity minus infinity. So does anyone have any techniques to simplify this? Or do something to manipulate this to get it in a form we can deal with? Very good. A multiple top and bottom. Not quite the reciprocal, because reciprocal is 1 over something, but I think conjugate or the I think you're using, I think you have the right idea, maybe just using the wrong word. We're going to multiply top and bottom by the conjugate of this expression, right? So now I have infinity plus infinity, which is infinity. So if I multiply top and bottom, I get the limit as infinity goes to, or sorry, x goes to infinity of x squared plus x. The middle two terms cancel, and then I'm minus with minus x squared, right? And then on the bottom, I still have x squared plus x plus x. So if I clean this up a little bit, Get the limit as x goes to infinity. The x squareds cancel, and I'm left with x over the square root of x squared plus x plus x. I could apply L'Hopital's rule here, and it would get messy. It would get pretty complicated. So does anyone have another approach?
Divide what's then by the highest power of the denominator.
Very good. What's the highest power of x in the denominator? The square root of x squared. How could I write the square root of x squared? Absolute value, right? So it turns out the square root of x squared can be rewritten as the absolute value of x. And the absolute value of x can be replaced with x when x goes to positive infinity. So now I'm dividing top and bottom by the absolute value of x. It's going to be a lot easier to make a conclusion versus L'Hopital's rule. Anytime you have a rational expression, you're going to want to use this technique instead of L'Hopital's rule. L'Hopital's rule, if I differentiate this, I'm going to have a 1 on top, which is all nice, but on bottom I have a mess. And I have a fraction on bottom. So I have 1 over a fraction. So I have to find a common denominator, flip and multiply, and then apply L'Hopital's rule again, and somehow cancel this, which is always going to be there, right? In some form or the other. So this is really the best approach. So if I take the limit as x goes to infinity, if I divide top and bottom by the absolute value of x, go ahead and write out some steps here, since it's been a while since we've seen this, right? So I can replace the absolute value of x in the numerator with just x. So I have 1. The denominator, for this expression, I replace the absolute value of x with the square root of x because it's convenient. So then this would be the square root of 1 plus 1 over x. Do you guys see where that comes from? If I replace it with the square root of x, then I have the square root of x squared. I have 1 plus 1 over x. And then here, I can just simply replace it with the absolute value of x. The absolute value of x with x, so I have plus 1. So then what's the limit? 1 over the square root of 1 plus 0 plus 1. So that gives me 1/2. You're a lot better off when you have a radical to use this technique. Right? Amanda?
Can you explain again how you did you got 1 over x under the square?
So here, really what I have, the square root of x squared plus x, and then I replace the absolute value of x with x squared. But when I don't have the radical, I just replace it with x. Right? If I have a plus b over c, I can write that as a over c plus b over c. That's just what I did here. So I changed my c to look like the square root of x squared when I divided by a.
You can put the square root or the square under the radical because it'll come out to be
Yeah, if I have the square root of a over the square root of b, I can write that as the square root of a over b. So yeah, since it's the square root of x here, I can just pull it under this one radical and get 1 plus 1 over x. And then this would be 1, so this would give me 1/2. So you'll have a chance to write that up later. Okay. So the last technique we're going to talk about is when we have the form, the indeterminate form, 0 to the 0 power, 1 to the infinity power, or, let's see if I can find them all. Here we go. Indeterminate forms. So indeterminate forms of type 0 to the 0, infinity to the 0, or 1 to the infinity. So these are 3 types that we're going to have to use logarithmic differentiation to solve for what the limit's going to be. So an example, we've seen this example multiple times. The limit as x goes to 0 from the right of 1 plus x to the 1 over x. Do you guys remember what this was? E, right? We looked at it different ways. We've looked at it this way. We've also looked at it as like v goes to infinity of 1 over v to the v power. But this is e. And we're going to show that this is e. But first I want to kind of evaluate a general form. So general form is going to be y equals an f of x to the g of x power, right? So if I want to find the limit as x goes to a of y, I really need to look at the limit as x goes to a of ln of y, which would be the limit as x goes to a of g of x times ln of f of x. Does everyone see where I got that? Right? If I take ln of both sides, I can rewrite, so I'm looking at ln of y. So if I take ln of this function, I can bring the g of x down and have g of x times ln of f of x. So if I can find the limit of ln of y, then the limit of y is going to be e to that number, right? So this is going to be e to the limit as x goes to a of ln of y. So I'm going to be able to find this, and then once I find that, if I want to find the original limit y, then I'm going to take e to that power. So let's look at an example like here. So I let y equal 1 plus x over, or sorry, 1 plus x to the 1 over x power. I can't begin to find what the limit of y is, but I can find the limit of ln of y. If I can find the limit of ln of y, the limit of y would just be e to that number. Right? So I'm going to say ln of y equals 1 over x times ln of 1 plus x. You guys remember doing this? So if I want to evaluate what would be the limit as x goes to 0 of ln of y, well, that's the limit as x goes to 0 of ln of 1 plus x over x. So this is type 0 over 0, right? So I'm looking at the right side limit, but if I plug in 0, ln of 1 is 0, and then x is going to 0. So this tells me I can apply L'Hopital's rule. I get the limit as x goes to 0 from the right of 1 over 1 plus x over 1. 1 over 1 plus 0, which would be 1. Now this is the limit of ln of y. So the limit as x goes to 0 from the right of ln of y equals 1. So if I take e to both sides, I get the limit as x goes to 0 from the right of y equals e to the first power. So we've shown this multiple times, right? We've seen it various different ways, but now we've shown it with L'Hopital's rule, that the limit of this is e to the first power.
I think I'm with you, but then in the part where you were like showing us how we derived it up over on this side,
Yeah.
is that e to the limit of x approaching?
Yeah, this is just a number, whatever. So I can't begin to look
That's
at
what represents the
what we
exponent of
find.
e.
Yes.
Okay.
Yes. So here we found it to be 1. So the limit of y is e to the 1. If we found it to be 5, the limit would be e to the 5th. If we found it to be infinity, the limit would be infinity.
What's that E on the left bottom corner?
This e? This e, I'm saying e to this power, e to this power. So if I take e to this power, it cancels the ln. and I just get y,
Okay.
right? Because e to the ln of y is just y. So that's how I get rid of the ln. Let's look at another example of this one. So this, I don't remember what number this is, but let's get as general as we can get. So pull this up here. Okay, so let's look at how would I go about finding the limit of a function that looks like, looking for the limit as x goes to infinity of 1 plus a over x to the bx power. So surely if we can do this one, we can do any one where a is any number and b is any number. So a and b are real numbers. So I'm going to let y equals 1 plus a over x to the bx power. So ln of y would be what? Very good. Bx times ln of 1 plus a over x. So if I want to evaluate the limit as x goes to infinity of ln of y, I get the limit as x goes to infinity of, maybe I'll write this as b times ln of 1 plus a over x to the minus 1. Huh?
The x to the
Yeah.
minus one.
Why did I do that? Yeah, to get it in a form where I can apply L'Hopital's rule, because right now I have infinity times 0, right? If this is going to infinity, then x goes to infinity, and ln of 1 goes to 0. So I have 0 times infinity. So I need to move 1 to the denominator to get it as infinity over infinity or 0 over 0. In this case, I want infinity over infinity, oh sorry, 0 over 0.
Why do you simplify the ln by 1 over 1 plus 8?
Why did I simplify it?
Yeah, like ln of that should be like 1 divided by 1 plus 8 divided by 8. What about if you do it that way?
If I find a common denominator?
No, like differentiation of the ln of the...
I can't differentiate it until it's in a 0 over 0 or infinity over infinity type. You cannot use differentiation until 0 over 0 or infinity over infinity. Anytime you have 0 times infinity, eventually you can apply L'Hopital's rule, but you have to get in the right form first. So I cannot differentiate until I have it as 0 over 0 or infinity over infinity. Make sense?
Mhm.
Okay. So now I've got it in the true form where I can differentiate. So I'm going to say, okay, I'm going to apply L'Hopital's rule. And I'll have the limit as x goes to infinity. So I have the b, because it's just a constant. What's the derivative of ln of 1 plus a over x? 1 over that, right? Times the derivative of the inside. What's the derivative of a over x? Minus ax to the minus 2, right? Because this is really ax to the minus 1. And the derivative of the bottom would be minus x to the minus 2, right? Nice that the negative cancels and the x to the minus 2 cancel. So what do I have left? I have the limit as x goes to infinity of ba over 1 plus a over x. So that's b times a over 1 plus 0, because x is going to infinity, so this a over x goes to 0. So I get b over a. This is the limit of ln of y, and I want to know what the limit of y is. So the limit as x goes to infinity of y would be e to the ba, or ab, which is just a number. So when a is 1 and b is 5, you get e to the fifth. And you can go through and see the same thing there. And
So we can just use that.
if I give you one like that, that's fine.
Just I wonder why you didn't move the x coefficient, which is b, to the denominator with x.
If I did, I would have to have b over 1, or 1 over b, right?
Mhm.
So it's easier just to leave it in the numerator because it needs to stay in the numerator. If I would have moved it in the denominator, I'd have 1 divided by 1 over b, which is a little bit more annoying to see. It's still b in the numerator. So any constants I can just leave out front. I could pull this constant out front of the limit altogether. And then when I take it, it's still going to be b times a, because everything else goes to 1. Right? So 1, if I remove the b, a outside, this would go to 1, and then this would be 1 plus 0. So the whole thing would go to 1, so it would just be b times a. You have that choice. Yeah. You want to simplify it as most as you can and still get in the form 0 over 0 or infinity over infinity. So bringing constants down doesn't help anything. All right. Let's look at number 34. If I have the limit as x goes to 0 of 1 minus cosine of 3x over x squared, and make a conclusion what this is going to equal.
0.
Huh?
0 over 0.
No. Well, it is in the form 0 over 0 right now. But 0 over 0 is never an answer. You got to simplify it. So it is 0 over 0, so you can apply L'Hopital's rule. So if I take the derivative of the top, what do I get?
That will be sine 3 times 3 sine 3x.
Good. 3 sine 3x. The derivative of the bottom, 2x. So if I plug in 0, I still get 0 over 0. But at least I know I'm kind of going somewhere, right? So if I apply it again, what do I get? Ideally, if you write this down.
Cosine x divided by 2.
I get what?
9 cosine of 3x over 2.
Yeah. Right, because I have that other, when I differentiate, I have 3 sine of 3x. And when I differentiate that, I have 3 times 3 cosine of 3x, right? So you had to be careful with that. So I think most of you got that. This is type 0 over 0. If I apply L'Hopital's rule, I get the limit as x goes to 0 of 3 sine of 3x over 2x, which is still type 0 over 0. But if I apply L'Hopital's rule again, I get the limit as x goes to 0 of 9 cosine of 3x over 2. Cosine at 0 is 1. So this is 9 times 1 over 2, which is 9 over 2. And there's your limit.
How did you get that?
Here, when I differentiated sine of 3x, I get 3 cosine of 3x. So this is really 3 cosine of 3x, right? Because the derivative of sine of 3x is 3 cosine of 3x. So I have another 3 out front. So that's 9. So derivatives are important. Being able to differentiate, just any random function is important, but on top of that, being able to apply differentiation in a limit problem. See if since we have some time in class. If I pull up some Wiley problems in this section. 3.6. So you should be able to make a conclusion here. Pretty straightforward, right? What's the limit going to go to? 0, right? I have a polynomial over e to the x. The polynomial, if I differentiate it enough times, eventually that goes to a constant. And then e to the x is always going to be there. So I have a constant over infinity, which goes to 0. Here, this is where you need to know the form for sine inverse. So if I plug in 0, I get 0 over 0. So I need to differentiate this sine inverse function. And the derivative of x is 1. And then I apply x go to 0.
You also put in the formula for sine inverse.
Mm-hmm. What's the formula for sine inverse? The derivative of sine inverse.
1 square root of 1
Minus or plus? Yeah. So if I have the derivative with respect to x of, let's call it u, sine inverse of u, I get 1 over the square root of
1 minus u squared.
u squared times du over dx, right? U is a function of x. So keep in mind that 4 is going to play a role there. Right? So yeah, it would be times 4. And then this 4x would be squared.
And then that whole thing would be over.
1. Right? And then if x goes to 0, then you see this term goes to 0. So you have basically 4. But if you don't take the derivative of the inside, you lose that. Okay. So this is infinity times 0, right? Which one is most natural to bring to the denominator? E to the negative x, right? Because you're going to write that as e to the positive x when it's in the denominator. So you have 6x over e to the x. So what's that going to go to? 0. 0, right? Because once I differentiate the first time, I am left with 6 over minus e to the minus x. So I have 6 over something going to infinity that goes to 0. So that concept can be utilized in multiple approaches. It might not always be a polynomial over e to the x. It might be something like this. So what is the most natural one to pull in the denominator? Secant, right? Write it as cosine. So you have cosine of 9x over cosine of 7x. So cosine at pi over 2, you think of either the graph, cosine at pi over 2, 0, or you can think of the unit circle at pi over 2, cosine with 0. So you have 0 over 0. You have to have an indeterminate form to apply L'Hopital's rule. You have an indeterminate form, so right now you have infinity times 0, but if you pull the secant down and write it as cosine, you have 0 over 0. So you can apply the L'Hopital's rule.
Excuse me. From the left or from the right?
Yes.
Does it make difference?
In this case, it could potentially, the limit doesn't exist at pi over 2. Because 1 goes to infinity, 1 goes to minus infinity, right? 1 over 0 from the left goes to positive infinity, right? So if I look at this graph and I'm approaching pi over 2 from the left, I'm always above that. But I'm going closer to 0. So I have 1 over something going to 0 positive goes to positive infinity. But if I approach it from the right, I go to minus infinity. So the limit doesn't exist at pi over 2. But the limit is going to exist at the left side of pi over 2. And on the right side of pi over 2 as well. But the limit at the point is not going to exist. Does that make sense?
Makes sense.
Okay. Yeah, so a lot of times with trig, it will be one-sided limits because the limit doesn't exist at that point. But you can still talk about the right side or the left side.
Kind of like how, this can be related, though, to what you were saying on the practice and the final.
Mm-hmm.
These types of problems are going to be like later on now, and so we're going to definitely get a left or a right side limit.
Possibly.
Where before, if there's the left and the right side limit don't exist and it asks you for the limit at that thing, then the answer is does not exist.
Correct. If the right side limit and the left side limit, you're always going to write something. Infinity, minus infinity are numbered. But the limit at a point might not exist based on the right side limit and the left side limit. But here, yeah, you're not going to have to check that
Right.
if it just gives you a left side limit. This is an example. You can see the one that we did in class with A over B, what the answer is going to be. Will be, so rhymes with B. E to the something that rhymes with B. But you can also go through and show your work there and convince yourself you could go through that problem. And this is just another example. I have tangent of pi over 2. Tangent of pi over 2 goes to the infinity. So I have 1, because 2 minus 1 goes to 1. So I have 1 to the infinity power. So I need to evaluate that. And I can't evaluate it by itself, so I have to do logarithmic evaluation of the... I have to evaluate the limit of ln of y. So then I go through and find the limit of ln of y, so the limit of y is going to be e to that number.
Would you mind working?
Yeah, we can look at that one. This is like number 35, the written one that we did in class. So simplify it. You multiply by the conjugate, top and bottom by the conjugate. Don't try to apply L'Hopital's rule. Divide top and bottom by the highest power of x in the denominator. In this case, it's going to be the absolute value of x. You can rewrite that as the square root of x squared. Don't try to apply L'Hopital's rule here. And then this one is a straightforward evaluating the limit L'Hopital's rule problem. There's not too many steps here, but go through it and see how this is going to cancel. So let's look at this example, which might look a little intimidating in the beginning, but I don't think it's too bad. So let's look at number 31 on Wiley. I have the limit as x goes to 1 of 2 minus x times, or to the power 5 tangent of pi over 2 times x. So I have this. And if I evaluate the limit, I have 1 to the infinity power, which is an indeterminate form. But it's not an indeterminate form I can apply L'Hopital's rule directly to. So I'm going to let y equal 2 minus x to the power 5 times tangent of pi over 2x. So ln of y equals 5 times tangent of pi over 2x.
So did your limit just go away?
I am going to deal with it in a minute.
You
So,
don't have to carry the limit when we're doing that.
no. So here, I'm just saying I'm going to let y equal this.
Yeah, you're gonna let the limit of x to blah, blah, blah. equal
Yeah.
y.
No, I'm going to let y equal the function. I'm going to evaluate the limit of y, because that would be this. But I can't evaluate the limit of y right now. I'm going to evaluate the limit of ln of y. So now, when I get this in this form, I need to carry the limit as x goes to 1 of 5 tangent of pi over 2x times ln of 2 minus x. So here, tangent of pi over 2 goes to infinity, and ln of 1 goes to 0. So I have type infinity times 0. So I need to manipulate it. Cosine. Let's see what I want to do. I probably want to rewrite it as cotangent, because I know the derivative of cotangent. And defined at 1, differentiating the top. So writing this out, I can write it as the limit as x goes to 1 of 5 times ln of 2 minus x over cotangent of pi over 2x. Right? Because cotangent's 1 over tangent. So now, what is cotangent of pi over 2? That goes to 0. And ln of 1 goes to 0, so this is type 0 over 0. So I can apply L'Hopital's rule. Applying L'Hopital's rule, I get the limit as x goes to 1 of 5 over 2 minus x times minus 1. Minus, what's the derivative of cotangent of pi over 2x? Minus cosecant squared pi over 2x times pi over 2, right? So what is cosecant of pi over 2? 1? Cosecant, you go, okay, cosecant, It's 15, right?
How do you get cotangent out of it?
Because I brought tangent down. So if I bring tangent in the denominator, I need to write it as 1 over tangent.
Yeah, but
1 over...
I didn't know. I thought tangent wasn't defined.
Tangent's not defined at pi over 2. But we're not... It's the limit as x approaches pi over 2 type thing. Does that make sense? Because x is approaching 1 here. And so this is approaching pi over 2. So right side limit, left side limit, it's going to be okay when I differentiate it. Cosine is defined at pi over 2. So this is cosine. And 1 over cosine of x is secant. And then if I look at sine, the graph of sine, this is sine of x. And 1 over sine of x is cosine of x, right? So sine at pi over 2 is 1, right? So secant is 1 over 1. So here, on top, I get minus 5, 2 minus 1 over minus 1 squared times pi over 2. So now I got to clean up some stuff. So the negatives cancel. Flip and multiply, so really have 5 over 1 times 2 over pi. So it would be 10 divided by pi. Flip and multiply. So what's my answer? If the limit of ln of y equals this, what does the limit of y equal? Very good. So I should expect that this answer to be e to the 10 over pi.
So we'll have pi somewhere.
Yeah. So if we go back to Wiley, last 2 seconds, if I say e to the 10 divided by pi. Last time it wouldn't let me submit my answer, so I don't know if it will either. Submit. I've never had it do this before today, and today it won't.
I had that problem with
It might be because I'm using Firefox instead of...
Well, I've had problems with Internet Explorer with it too.
It wasn't working on Chrome, then it wasn't working on Firefox on 3.4. Now it's decided not to work on
Yeah.
Firefox.
It wasn't working on Firefox.
Is it just been something that's been recent?
Yeah.
Okay. I will submit an error to see. Obviously, it's not working. So I'll see if I can figure that out.
I will never know what is the right answer.
All right, I'll see you guys tomorrow. Keep in mind we're reviewing for the exam, so bring your review sheet. Yeah, Bethany or...
I'll try to start it earlier this time.